Okay, so like I said, I'll be talking about X-ray diffraction or XRD today. So today I'll be going over the history of XRD, so some of the big names that kind of contributed to the field. I'll be talking about the Bragg equation and how that relates. I'll be talking about how XRD actually works, and then I'll be talking about some of the common applications for XRD. So one of the biggest names we talk about when we talk about XRD is Max von Laue. And Max von Laue was a German physicist, and during his career he traveled around to many different universities in Germany. He studied at Strasbourg, Göttingen, Munich, and Berlin. And after his education was complete, he actually went back to the University of Berlin and he worked under Max Planck. And that name may sound familiar because Max Planck was the man who discovered the relationship between the frequency and the energy of waves, which resulted in the universal constant or the Planck constant. So Laue worked under Planck. And so then it was in Berlin that he worked on X-ray diffraction. And he had this idea that it might be possible to shoot an X-ray at a crystalline sample and then get a diffraction pattern because of crystal's ordered array structure. And so he presented his idea to Arnold Sommerfeld and Wilhelm Wien. And those two names might also sound familiar. Arnold Sommerfeld is a huge name in quantum mechanics. He came up with the theoretical structure of the hydrogen atom and elliptical orbitals for atoms. And then Wilhelm Wien has a Nobel Prize in the laws governing the radiation of heat. And they were at Sommerfeld's ski lodge. He had a ski lodge that he would often invite colleagues and students to come ski and talk about physics. And so they were at the ski lodge and Laue presented this idea to them and they actually rejected his idea. So then he went to two other colleagues, Walter Friedrich and Paul Nipping, and they knew a lot about creating X-rays and using them. And they thought the idea had some potential. So they ran the experiment and after some mixed results, they did find diffraction spots on their photographic plate. And so Laue's theory was confirmed. And so he won the Nobel Prize for that in 1914. And then in 1917, he actually became the second director of the Institute for Physics. And Einstein was the first director. And so Laue was actually very interested in Einstein's theory of relativity. So that worked out for him pretty well. And then he was also captured during World War II and taken to England with 9 other German scientists. And he wrote a paper on the low absorption of X-rays during diffraction there. And that paper was later contributed to Harvard University. And one really interesting thing about Laue is he had this reputation at all the universities he taught at. He loved anything high speed. So he was this esteemed professor. He had won the Nobel Prize, but he would always zoom into campus on a motorcycle and teach a lecture, which very interesting. So this is the technique that Laue came up with. As you can see, this is the X-ray, this is the instant X-ray, and it's a white X-ray, so it has multiple X-rays of different wavelengths, and so then this is the crystalline sample, and then the X-rays are scattered, and the results are collected on a photographic plate. And as you can see here, this is simplified, but these are the diffraction spots. So looking a little closer, this is the diffraction pattern for sodium chloride or just table salt. And obviously we don't just do this because it looks pretty. There's a reason. We can get information about the structure from this diffraction pattern. In some cases, the pattern of the diffraction pattern, the symmetry can indicate symmetry of the crystal structure, the unit cell. And over here I have some examples of some unit cells and different planes. So if the diffraction pattern, for example, maybe it had 4-fold symmetry, the unit cell might also have 4-fold symmetry, or the plane might have 4-fold symmetry. But that is just a very simplified way of explaining it. The math is way beyond the scope of this presentation, but it's important to know that we can take this diffraction pattern and we can determine whether the structure is cubic, hexagonal, tetragonal, etc. So then the second names that we talk about when we talk about XRD are William and Lawrence Bragg, who are father and son. And William Bragg was a British physicist, and he attended Trinity College, Cambridge. And then during his career, he moved to Australia, where he had his son, Lawrence Bragg. And Lawrence attended Adelaide University in Australia. And then the father and son pair moved back to England And Lawrence attended the same college his father attended, Trinity College. And so then it was in England they started to work on X-rays and crystal structure. And they came up with what we know as the Bragg equation, 2d sine theta equals n lambda. And so that equation just kind of describes the conditions that need to be met for diffraction. And so they won the Nobel Prize for that in 1915. And some interesting things about their Nobel Prize: they're one of 4 pairs of parent and child to win a Nobel Prize, and they're the only pair that won it together. And then Lawrence is still the youngest person ever to receive a Nobel Prize. He was 25. And then shortly after that, they kind of switched gears, and in World War I, they were locating submarines using sound. So kind of different from X-rays and crystal structure, but cool nonetheless. And then something interesting about both of them, they were both knighted at different points in their lives. William in 1920 and Lawrence in 1941, and they were knighted for their scientific achievements. So they became Sir William and Sir Lawrence. So then their technique we call diffractometry. And so talk about how it works. So obviously to have XRD, you need X-rays. So the X-rays are produced via a cathode ray tube. You can see that here in the diagram. And then the X-rays are one wavelength in this technique. They're not multiple, it's a constant one wavelength. So the X-rays are directed at the sample. You can see here it's the sample is random crystals. And then the incident X-rays are reflected into the detector. And so then if I hit play on this video, you'll see that the crystals and the detector will rotate. And what this does is this provides a range of angles for which the incident X-ray will hit the sample. And so if we look down at the Bragg equation, D is just the distance between the diffracting planes of atoms in the crystal. Lambda is the wavelength of the X-ray, and then theta is the angle of the incident X-ray that hits the sample. And so when this relationship is satisfied, we get a peak in the graph. The graph has theta on the X, that's the angle, and then we have the intensity of the reflected X-ray on the Y. And so when this relationship is satisfied, we get a peak. And so then I can hit play again. And so the animation will pause momentarily when it hits a peak. And there's one. Yep. So when that relationship is satisfied, we'll get a peak. So obviously, staring at this graph won't do anything. We have to actually interpret it. So there are many things you can get from an XRD graph. Just one example, you may be able to figure out what an unknown sample is made of. So you would take your XRD graph and you would take it to a library or a database, and you would match the graph. You'd match the peaks with graphs of known materials, and you would try to figure out what your unknown sample was made of. But that's just one example. So this diagram kind of helps us get a better look at what's happening on the surface of the sample. The sample, here we can see the blue dots are the atoms, and you see they're arranged in planes. And then the green wave and the black line, that's the incident and reflected X-rays. And what I really like about this diagram is that it has this green wave feature. Most diagrams don't have that, but it's the wave behavior of X-rays that allow us to actually have diffraction. If the X-rays were just a straight line coming in and bouncing off, we would not have diffraction. We need this wave behavior. So looking closer at that wave behavior, here I just have an example of an XRD graph. I don't know what material it's for, but it's just an example. I have the Bragg equation. And you may remember maybe from high school physics or other physics classes, when we talk about waves, we talk about how they interact. And so with waves, we can have constructive interference, where the waves are in phase with one another, and the resulting wave will be of a higher amplitude. And we can have destructive interference, where waves are out of phase with one another, and we'll get a wave with a lower amplitude than what we started with. So what's happening is when the Bragg equation is satisfied, when this angle is correct, that's when the reflected X-rays are constructively interfering with one another, and that's where we get a spike in intensity in the XRD graph. So that's where our peaks come from. So then just some common applications. So like I said, we can determine lots of things from an XRD graph, and these are just a few of the examples, some of the big hitters. So we can determine multiple properties of a sample, the structure, phases, crystallinity, strain, and many more. We can identify unknown samples. I talked about that earlier. We can match graphs to other graphs in libraries or databases. We can characterize thin film samples, and we can measure sample purity or find defects. One of the really good examples that in a webinar that I watched that Dr. Singh sent to me was this team had 3 pieces of jade, and they wanted to see if the jade was real jade or not. And real jade is made up of jadeite and nephrite and has not been treated for defects. You can also have fake jade that has been treated for defects, or you can just have quartz that's been colored green. So they did XRD on each of the jade samples, and the first one turned out to be just quartz that had been colored green. The second turned out to be jadeite and nephrite, but the XRD graph suggested the presence of another material, which meant it had been treated for defects, so it was closer, but not real jade. And then the final turned out to be 100% real jade, which is interesting. And like I said, obviously, these aren't the only things we can do with an XRD graph, but these are just some of the big hitters. So I hope you enjoyed this. Any questions?
Thank you so much. Very nice presentation.